I'm Steve Russell, power semiconductor subject matter expert at Tech Insights. So a couple of days ago, Tesla had their Investor Day on March the 1st, 2023. Here they announced multiple optimizations to the future manufacture of their electric vehicles. The most eye-catching of these from a power semiconductor perspective was they will reduce the amount of silicon carbide in future vehicles by 75%, with Tesla VP of Powertrain Engineering, Colin Campbell, stating, "The silicon carbide wafer that's inside those packages can be much smaller. Silicon carbide is an amazing semiconductor, but it's also expensive and it's really hard to scale." In early trading the following day, Wolfspeed shares had fallen 12%, with STMicro and onsemi both falling greater than 5%. How bad is this for silicon carbide manufacturers? First, I think it's important to note the positive tone of the quote. Silicon carbide is an amazing semiconductor. I concur. Silicon carbide is undoubtedly the future of EV drivetrains, and that future is very bright. There are a lot of ways to reduce the amount of silicon carbide through optimization. Indeed, the silicon carbide die can be much smaller. Taking one example of a silicon carbide MOSFET manufacturer with significant historical design wins in Tesla cars, STMicroelectronics. At the end of 2022, ST released their third generation ST Power silicon carbide MOSFET, which is automotive qualified. We have completed a full suite of reverse engineering analysis on these devices. One standout point to note is the 40% reduction in specific on resistance normalized to the MOSFET array that we have observed moving from their second generation to third generation product. Keep in mind the silicon carbide in existing Tesla vehicles will be at least a generation behind. Right away, this loosely translates to 40% less silicon carbide required for the same current. ST achieved these savings by a cell pitch shrink combined with segmenting P+ body contacts along the source array, all while sticking with the more conservative planar gate MOSFET array, as seen here. Trench designs can provide even further efficiency savings. Colin Campbell also discussed moving forward, Tesla has designed their own thermally optimized package. Details of this are yet to be revealed, so specific efficiency savings are difficult to state at this stage. But, in principle, this means the silicon carbide devices within can be driven harder. Note ST's third generation silicon carbide MOSFETs are already rated to 200 degrees centigrade, the highest available in the market, and beyond what silicon is capable of. Silicon carbide as a material does not become intrinsic until well over 500 degrees centigrade, so there is in fact a huge amount of room to grow here. It is the packaging, wiring, and contacts that really need to catch up to the silicon carbide. There are more novel approaches to the reduction of silicon carbide material. Despite silicon carbide MOSFETs having their own internal body diode for reverse conduction, they are commonly co-packaged in module configurations with additional silicon carbide Schottky diodes to improve system robustness. Toshiba is the first silicon carbide manufacturer we have observed taking this approach of integrating a Schottky diode into an active silicon carbide MOSFET array, seen in the cross-sectional example here. This increases the silicon carbide MOSFET die size, but in fact reduces the overall amount of silicon carbide necessary at a system level. We expect many more manufacturers to go down this route over the coming years. Some final points to note. Tesla does estimate a 75% reduction in silicon carbide per car for their next generation vehicle, not affecting current production cars. They also plan to increase the amount of EVs produced to 20 million per year, a 20-fold increase. Now granted, this is an ambitious target, but with the ever-growing new entrants using silicon carbide in the EV market, I wouldn't be panicking just yet about the prospects for silicon carbide. At Tech Insights, our forecast shows silicon IGBTs maintaining the largest share of volume for some time, but silicon carbide penetration approaches around 38% in 2029. Subscribers can access our reverse engineering ports on ST and Toshiba silicon carbide MOSFETs, as well as market analysis including the global xEV system, semiconductor and sensor demand forecast 2020 to 2029, all on the Tech Insights platform.